Welcome to a geometric conjecture. Here we render the electron, down quark, and up quark. Each map transposes as a toroidal surface, and although each particle is defined as a wave function, we can conceptualize it housed within the torus and not argue the semantics. And to avoid unnecessary complication, we only need to utilize master map 1, whereby we discern zone 1, analogous to the neutral Z boson, and zones 2 and 3, each analogous to the charged W bosons. We'll begin by isolating the composite electron, depicting its constitution both as a colored and as a green composite map for visual clarity. 174 knots in total. Yet it does not reside in any particular place. Instead, our 4-component electron manifests in 6 positions, eventfully, making our master maps most unlike the periodic table of elements. We can't simply say, there it is. We'll denote the 6 positions, sequencing over 4 pi rotation, as 1, 2, 3, 4, 5, 6, and back to 1. So if we say the spin-up electron is in position 1, then its spin-down companion will be 2 pi radians apart in position 4. Both will reside with opposite spin in zone 1. Note that spin-up or spin-down is a verbal convenience. Maps are purposefully notated spin plus or minus a half, reminding us that our concept of spin, likewise charge, is relative, such that if we say spin up is in position 2, then spin down will be in position 5, both residing in zone 3. Or if spin up is in position 3, then spin down will be in position 6, both in zone 2. Take a moment to witness this resolving of the quantum world. For we can discern our 4 components as the right chiral electron, noting the lack of interaction with the gray shaded regions of the Z and W bosons. The left chiral anti-electron, also noting the lack of interaction with the Z and W bosons. The right chiral anti-electron, this time noting its interaction with the gray shaded bosons. And the left chiral electron, again noticing its interaction with the gray bosons. Both left and right chiral electron are bound through a common node, circled red, whereby knots converging in each nest share common codes with those diverging in the corresponding trunk. Similarly, both left and right chiral anti-electron are bound through a common node. Only this time, we see the left chiral anti-electron diverge throughout each branch, and the right chiral anti-electron diverge throughout the corresponding trunk. We'll now render the relative mass of the electron, utilizing the right chiral component in position 1 and associated F1 knot. This knot appears as a node or conduit between the other components and between master maps. It also has a speculative association with the neutrino. Each color represents a weight such that 2, 3, 8, 6, 3, 1, 2, 3, 2, and 3 add up to 33, the relative mass of the electron. In similar fashion, the relative mass of the down quark is rendered by utilizing the right chiral down quark component and associated A1 knot. And again, each color represents a weight such that 2, 3, 4, 8, 3, 2, 1, 3, 2, and 3 add up to 31, the relative mass of the down quark. Likewise, the relative mass of the up quark is rendered by utilizing the right chiral component and associated B1 knot. However, this time, each color represents a weight such that 4, 3, 2, 2, 3, 2, 2, 3, 3, and 3 is 27. Now that's the relative mass of the bottom quark, not the up quark as we may have expected. So here we expose a profound feature of master maps. Just as the relative boson mass is embedded in the knot precession between zones, so too does magnitude precess. And we'll save the details for another video, else this one be unwieldy. Suffice to say, it's a profundity like no other. Recalling master maps are most unlike the periodic table of elements. Here we'll simply add position 1 and position 4 component weights, or 2 lots of 27, plus 94 and 6, the central boson weights and associated green knot. So we have 54 plus 100 is 154, the relative mass of the up quark. Just as we isolated the composite electron, depicting its constitution both as a colored and as a green composite map, we'll isolate the composite down quark both as a colored and as a blue composite map. Likewise, the composite up quark both as a colored and as an orange composite map. And we'll juxtapose them to get a better sense of their relative positions, coloring them green, blue, and orange for visual clarity. And we find certain knots constituting more than one particle, making it difficult to portray them in a single map. Yet despite losing some detail, we'll settle on the yellow knots, best representing this entanglement of the electron down quark and up quark. Interestingly, these 136 yellow knots are a commonality with all observable matter, and their total weight is 432. We'll conclude this video by animating the 3 particles in each master map, noticing that they either converge into a nest or diverge into the corresponding branch or trunk of some other map. Recall that each of these spin 1/2 components is in a superposition or entanglement of 6 positions. Therefore, we ascertain a particular pattern of behavior for whatever it is we're looking for. In so doing, we constitute and thereby substantiate it. Herein, the outrageous complexity, albeit simplicity, of nature.